Hi, welcome to part 6 of my low temperature disconnect switch for lithium batteries. I would like to talk about a couple of things. I have managed to find a box in the somewhere in my house, and I put a little metal plate, and then I put the 3 switches on it, and also installed the Arduino, a fan. We need to connect that fan also to the Arduino. I haven't programmed it yet, but now we know what the second temperature sensor is for. Okay, then I used one of those boards here. I hope I can fit everything on one board, and I will see. So this is what I did so far with the box. Then I got some parts for the power supply. I got those parts from an old board from a television, an LED television. I put it in the oven, you can see, and I forgot to take the capacitors off, and it started to stink horribly. So if you ever do that, first put the capacitors, take them off, and then you can put it in the oven and all the parts come off. All right. So today we talk about the power supply, and there's one little problem we have, because we cannot take the power from the battery and then in the same time disconnect the solar panels from the battery, because if the batteries run low, how can we get the power to switch the IGBT, the switch, on again if we don't have the power anymore? So we have to use the power from the solar panels, and we cannot use the power from the battery charger either, because often the battery charger has a little output, because also this output is switched off when the batteries run low. So this is one important thing. We have to draw the power from the solar panel. Okay, we can use a separate solar panel. If we use a separate solar panel, then we can use a quite affordable, cheap DC-DC converter to, this is one of those little bricks. This one here is, I found this on eBay. It's quite cheap. It was like $6, and there is a lot of electronic in it. And this converts something between 36 and 75 volts, I think, into 12 volts. I'm having a solar panel here. This is an 18-volt solar panel. Okay, it's certainly too small, but 4 of them actually would be big enough, and we could run those 4 panels on a cheap DC-DC converter, and we get our 12 volts, and we are in business. I, for myself, went with another solution. I went with a solution to use a higher quality DC converter and hook this up straight to our solar system. I bought 2 of them. One I have right here for testing, and the other one is still here in the box. This little DC-DC converter is around $50. It's from a European company, Gaia. I think it's a French company. And then I got from this company, Recom, actually for testing purpose, really high quality half bricks here. And this one is a 40-watt brick. I could use this one too. Actually, they are both, the Gaia and the Recom, they are both built normally for military purpose or for train appliances, because there are a lot of power fluctuation, and it's a very dirty electricity, and for that reason you need a very high quality DC-DC converter to power your systems, your electronics. But the second very nice and special thing about these two systems, Gaia or Recom, this Gaia puts out 2 times 250 milliamps by 12 volt and 2 times 200 milliamps by 15 volts. And this one, of course, 40 watts, it puts out 24 volts, 2 times 12 volts by 3.5 amps, what is fantastic. Actually, I think I like this so much that I won't use it for that project, maybe use it for another project. But they are performing more or less the same. Of course, this is higher amperage, but they're doing quite fine, both of them. So what is so interesting with these pieces is that they have a voltage input range of like 12 volt to 160 volts. 160 volt from both is the maximum. That means actually whatever DC you put in, it will make 12 volts. The second good thing about this piece is that let's have a look at the data sheet, that it has a hysteresis, or how you say, a deadband. It switches on at around 12 volts and it switches off at around 9 volts. That means up to 9 volts or 9.9 volt. We check that together, what the voltage is. In that area, it puts out already 12 volts. That is really, really nice. We hook that up to our solar system and we are in business. The second thing, it's galvanically isolated. That's another important thing, because in industry standard is that we have everything galvanically isolated. I want to read something from the data sheet, what the quality is of those DC converters. Okay, it has an LC filter built in. Imagine we have solar panels and we have a long cable, and this is like a huge antenna, and the thunderstorm is coming and it's picking up all kind of shit. At the next point, we have to filter that out again. Actually, that's why I got this electronic parts. We have to build a filter in front of the input that looks a little bit like that. And we have to filter the output a little bit, and then inside again is a very high quality LC filter. It has a soft start function, what is nice. It has low voltage protection. It is short circuit protected, what is again a very good thing. That means it's overcurrent protected. And it has an over voltage limitation. That means if there's higher voltage than 160 volts, it will also protect the system from that and switch off. So I think this is exactly what we need for our purpose, to hook, to draw the power from our solar panels. Because of course in the morning the sun comes up, we have 0 volts, and and if we disconnect our disconnect switch, we can get quite a high voltage and make sure that everything works fine. And for that reason, we have, of course, several functions built into not only the power supply, also in the program in the Arduino. So we will stay in our common range. And the last thing, what I want to show you is that these DC-DC converters, they have an on state or an off state. They don't do funny stuff. If you use a 78.05 or something like that, a regular voltage regulator, then there's a certain point where it starts working and stops working, and at that point the regulator does a lot of funny stuff, and this funny stuff it puts out, this can screw up your processor, your CPU. That is actually another big problem, and to prevent that, we use a high quality part. And I have prepared, now here's something, I'm putting out 12.5 volts. This is the 15 volt piece, and I'm getting out exactly 15 volts here. I adjusted it, and the probe is times 10, so we can see that. If I turn this now down at a certain, I go down in millivolts here, in 10 millivolts steps I go down, and at a certain point we can see, so it's still on. At a certain point, it shuts right off. 9.7, I didn't want to go down now. Step by step, it would have taken forever, but it shuts off, and that's it. And the same is at the on point. Low, it goes up, and click, we are back on. That is really a nice thing. We don't get any funny stuff coming out of these inverters, and this is what I like. So we have 11.7 volts, and we get our 15 volts already out here. So if we look precisely, then we see that there is something going on here. There are all these little spikes. So I turned this up a little bit, and we can see that there is a whole lot of shit going on, and for that reason we also need to add in the output some capacitor or LC filter for filtering. So if I put the capacitor on here, you see the spikes are gone, and we have just the noise. It works quite fine. So now let's have a look. Normally our solar cells are connected through 2 cables and some breaker stuff directly to the charge regulator. We have only to take off one wire. This is the negative wire, and we connect this negative wire to the IGBT on the emitter. So we have a look at our IGBT, and we see we have these 2 terminals. This is a backup terminal, and we connect it to the emitter on the IGBT, and the other one, it's this or this, I have to look. The other one, we connect back to the charge regulator. And that's all we have to do to connect our low temperature switch to our system. Okay, we need one more cable, that's a positive power supply for our low temperature switch. So we run a little wire from the breaker or fuse, or from the charge regulator, from the positive wire, we pick up with a little wire, a thin gauge wire, we pick our positive and run it also to our low temperature switch. So our negative we pick up from the terminal on the IGBT, and our positive we pick up at the fuse or at the charge regulator. And that's basically it. So we have these two wires. This is the gate that drives the IGBT. We get to that later. So we have these 2 wires, no more. And these 2 wires, they go to a couple of discrete components. All these components are protection or filtering. This is a varistor that has at a certain voltage it conducts. So I think it's like 300, 400 volts, something like that. It starts conducting. It's nibbling down this too high voltage noise. Then it's a little fuse here, then a protective diode, and then we get the first capacitor, a coil, a second capacitor, and a special diode. This diode works a little bit like this varistor. From there, we just go into our first DC converter. It's an isolated DC converter. We see that on the dotted line. We have 2 connections here. 3 is negative in, 5 is positive in. I could have used this brick from Recom, but I thought it's just a little bit too nice to use it for that. So I went with a cheaper and smaller DC converter. It's this one from Gaia. It has a couple of pins, but we use only a couple, 2 on this side and 4 on this side. We get out with 12 volt. We have this unit puts out actually 2 times 12 volts. So I paralleled these 2 pins, and I get the double current and get 12 volt out. And this 12 volt I feed the positive directly to the fan and a protective diode, and the negative I feed to a MOSFET. Then the negative goes back to the fan. And here I have a pull-down resistor and I have a current limiting resistor, and this is pin 9 from the Arduino, and it can switch this fan on and off. So this is our first circuit. On the fan later there is a little plug like this. I connect this to the fan and then I can plug it into my board. Okay, then the 12 volt continues. It builds a rail here. This is positive and this is negative. And on this rail I have 2 more DC converters. One is this one. You see there's no dotted line. It's not isolated. This is the converter that makes very nice 5 volt from this 12 volt. It has 3 pins. 1, 2 is run through. It's a ground, and 3. And this is very nicely regulated, much better than the voltage regulator on the Arduino can do. Okay. The second one is isolated. This is for the IGBT. It puts out a COM that's not a ground because it's isolated, and above the COM is 15 volt positive, and under the COM is negative 9 volt under it. And these voltages, these are the IGBT wants 15 volt to switch on and negative 9 volt to switch off. These 2 voltages we feed in to a IGBT driver. It's a little chip with like 8 pins. It also has an isolation, and it switches the 15 or the 19 volts to that pin here. I forgot to put the number. And it goes through a current limiting resistor to the gate and provides a gate with 15 or 9 volt. And that's it. That's the input for the switch from the Arduino. Pin also not there. And yeah, that's the whole circuit. That's it. I have already built the board. Here it is. It's a little cramped. I did this board without making a drawing first, just out of my hand, and if you can see, there's not one budge wire, and I don't know why, but if I do it out of my head, it just comes better than if I. Anyway, this is it. We can see that this power positive that comes from the breaker or the battery charger, and this is the negative. It picks it up just from the IGBT terminal. So here we have the varistor, the fuse, the first capacitor, the coil, the second capacitor, the special diodes. I didn't have one with the right voltage, so I used 2 in series. Then we get this Gaia and other capacitors. Then we get the fan output here, the resistors, the 2 DC converters, another 2 capacitors. By the way, I will change them. They're a little too big. And the IGBT driver. And that's it. On the back, we can see it's also not a big deal. It looks very nice. And 10 little thingies there, and it's all set. And I have put the, okay, I don't know if you can see that. I have put a little strip there. I can put these things here in, and like this, and connect the output and inputs directly with the Arduino. I did write down what's coming out of these pins. So I have 10 and 9, I have nothing. 8, I have the signal input from the Arduino output for the IGBT. Then on 7 I have the gate output for the IGBT. Then on 6 I have the COM. Remember the COM, we need to connect the COM with, where is the COM? Here, we need to connect the COM with the negative on here to make it grounded. Then I have again not connected. Then I have the 5 volt, the ground, the 12 volt, and the signal for the fan, and that's it. It's no more. And so we're done. Just for the fun of it, I wanted to show you one more time what these regulators can do. Let's give it some power. So this here is coming out of my cheap little power supply. I'm feeding like 19.5 volt in here. This is how it looks, and this is how it looks when it's come out of our new voltage regulator. You can see we have them both on the same voltage range, and that's how this looks like. Isn't that nice and regulated? That's the difference between good quality and Chinese shit. So that was it. Catch me next time. Bye.